In the past few videos, I've talked about how we can use the idea of a potential divider with maybe two resistors in series to produce a voltage that we want, whether it is to make a light bulb or to light up some lighting, or for a fire alarm, or to turn up some loudspeaker control. Now, in this video, I'm going to talk about how you can also use this potential divider, more specifically a potentiometer, to actually measure voltage. So let me start by drawing a battery. Some wires. Now this time I'm going to switch back to my long resistor. Not drawing it very well, but this is supposed to be a long and uniform piece of wire with a certain resistance, and this is connected to a battery. Now put in some values just to make it easier to understand. Let's say this is 1.5 volt, this is a 1.5 volt cell, and suppose that the length of this resistance is 1 meter, and that's the resistance. Resistance is, say, 9 ohms. Right, okay. Now the problem is this. Suppose that I have an unknown cell with an unknown voltage. Okay, I have this cell here, which I picked out from maybe some rubbish. I just happened to see a cell there, and I'm wondering if it would be useful, whether there's any more voltage left, or what voltage is. So I would like to measure this voltage. Now this is one way I can do it. Okay, now it seems a bit troublesome, but so why don't we just get a voltmeter and do it? Well, a voltmeter works in a certain way, and there are many types of voltmeter, and this is perhaps one of the possible way that the voltmeter works. So we are basically learning about one of the possible ways, one of the possible physical principle of measuring voltages. So I have this unknown voltage that I want to measure. How can I use this potentiometer to measure it? Okay, this is what I can do. I can connect this battery to one end of the long wire, and I can connect the other battery to a sliding contact, meaning just a wire with a bare end here that I can, meaning not insulated, and that are free to move up and down along this long resistor. Now why would I want to do that? Okay, see, the idea is that I want to put an ammeter here. Now as I right, let's say when this contact is at a certain position. Now, as we understand from the past videos. With a long resistance like that, we can think of this long resistance as having two parts, as having one part of the resistor here and another part of the resistor up there. So we can think of this sliding contact as dividing the long resistor into two parts, and this overall voltage of 1.5 volts would then be divided in a ratio between those two parts, a ratio that's equal to the ratio of the resistances. So if I slide this contact down, there'll be less resistance in between, and then these two ends would produce a smaller voltage across. Okay, so the idea of the potential divider is that one part of this resistor provides a certain voltage that is proportional to the resistance in between. Why would I want to set this up? Why would I want to do this? Okay, let me take a quick look at the directions of the current and the size of the battery. See, this battery here is positive on this side, and battery here is positive on this side. Okay, so what it means is that the current will flow in this direction. Current always flow from positive to negative. Okay, it goes from higher to a lower potential. So what it means is that if this section of the resistance produces a voltage, in earlier videos I've been calling this V2, and the voltage from there I call it V1. Now if there is a voltage V2 here, then across these 2 points, then this point must be like a positive pole, and that point must be like a negative pole. Okay, if I say that the potential difference, the voltage between this point and this point is V2, that must also mean that this part of the resistor acts like a battery itself that produces this V2 volts of voltage. Okay, so this part is like a battery with a positive pole here and a negative pole here. So it looks like I'm connecting an unknown battery to a battery, an unknown voltage to another voltage. So a battery to a battery with the positive and positive poles connected together. So this is like a battery that would try to produce a current in this direction. That battery tries to produce a current in that direction. So this V2 and this unknown, let me call it V3, is an unknown voltage. They both try to produce current that go against each other. Okay, these voltages are acting in opposite directions. Okay. Now, if it happens that this voltage is the same as this voltage, is equal and opposite to this voltage, then we would expect that the current will be zero. Okay, it's like equal and opposite forces cancelling each other. So that is the idea here. If as I slide this point up and down, I can change V2. Now if V2 increases or decreases until it becomes exactly the same as V3, then we would expect the current measured here to be zero. And that's the whole idea. I want to slide this contact up and down until I find a point where the current becomes zero. Okay, I want the current I here to become 0 ampere. The reason is that when that happens, I know that V2 is equal to V3. Okay, so if I can find V2, then I would know the unknown voltage of this cell. So this is the method. This is the method of using a potentiometer to measure, if you like, the EMF of a battery. And how would we know what V2 is? Well, we have already looked at this example before. The way to know what V2 is to think of this resistivity equation, which tells us that for a long and uniform piece of resistor or wire, the resistance is proportional to the length. So if let's say that the length of this distance is L, right, between these 2 points is L, the length of the whole wire is big L. So big L is the full length of the wire, and little L is the length between here and here. Try to draw it maybe between here and here. Okay. Then we also know that the resistance across each part of the resistor is proportional to the voltage across it. Since the voltage across the full resistor, the whole resistor, is 1.5 volts, it must mean that the 1.5 volt corresponds to the length L, and the whatever voltage V2 we have here is proportional to the length little L. So let me write this out. According to this formula, R is proportional to L. Okay, and according to Ohm's law, V equals to IR. V is proportional to R. Okay, as long as I is the same, which it is along here and here. So this means that the voltage is proportional to the length of the resistor. Right? The voltage across the resistor is proportional to its length. So therefore, we have this relation now, that the ratio of V2 to V, the ratio of this voltage to the full voltage, must be equal to the ratio of this length, little L, to the full length, which is the big L. So we have this ratio here because of the resistivity equation and Ohm's law. Now from this, we can now calculate V2. So V2 must be equal to L over big L times V. And with these numbers, we can actually find an answer. We don't know little L yet. Let me just take for example that little L is 0. Let's see, maybe 0.3 meters. Okay, so putting in the values, then I have 0.3 divided by 1 times the V is the 1.5 volts. 1.5, and the answer is 0.45 volts. So in this way, I have measured the EMF of this unknown cell.